Hello, this is Dr. K. In this week's recordings, we're going to talk about program memory and see how that relates to the notion of mutable types and immutable types. We'll end up by seeing how to trace through code at a very low level. These recordings do not closely follow your Horstman readings, but I think you'll find that they give you a better understanding of how to reason about the Java programs you create. In this video, we're going to talk a little bit about program memory. Now, we're just going to scratch the surface here, but I think understanding a little about program memory will help you with concepts like static fields, final declarations, and perhaps most importantly, immutable types. Let's get started. Most computer programs use 4 distinct areas of memory when they're running. One area of memory is where the code resides. Remember that a program is stored on disk until it's run. Then its instructions are moved into memory. Another area of memory is used for variables that will exist for the life of the program. In Java, these are variables that are declared as static. Yet another area of memory is used for variables and information that are associated with method calls. This is the stack. As methods are called, their variables and information are placed on the stack. When methods return, their variables and information are removed from the stack. Finally, the heap is used to store objects. Objects are accessed by reference variables that are stored elsewhere in memory, often on the stack. But objects themselves do not reside on the stack. They reside on the heap. We'll come back to the heap in a later slide, but let's take a closer look first at the stack. This is a very oversimplified example of what happens when methods call each other in Java. But it should give you a basic understanding of how the program stack works. The program stack is an area in memory. As local variables are declared in the program, their names and values get pushed onto the stack. For example, the red arrow indicates where we are in the program. In this case, we're about to call the method getAverage with arguments 2 and 6. We have declared an int variable named average, or AVG, to hold the result, but we don't know its value yet. Therefore, our stack contains the local variable AVG from the method main, but its value is unknown. And when we call the getAverage method, the 2 parameters n and m are placed on the stack. We know their values because their values are the arguments that the main method passed in, 2 and 6. Next, we declare a variable named sum, and we call the getSum method with n and m, which we know are 2 and 6. The arrow here indicates that we have declared the variable sum, but we have not called getSum to get its value yet. This is a good place to pause and try to figure out what will happen to the stack once we call the method getSum. Please pause the video. I'll give you 5 seconds starting now. Ready? When getSum is called, parameters n and m are pushed onto the stack. Note that the parameters m and n that are pushed are the parameters of the method getSum. The parameters of the method getAverage are already on the stack. In the next statement, the local variable sum is declared and initialized. Since the value that sum is initialized to is not a method call, it is evaluated right away. N and m are 2 and 6. 2 plus 6 is 8, so the variable sum gets the value 8. and that is added to the stack. Now we start returning things. When we return from the getSum method, we are returning the value of the local variable sum, which is 8. That will be assigned to the local variable sum from the getAverage method, the green one. Also, after we return from the method getSum, we don't need the local variables anymore. Therefore, they're removed from the stack. So after we return from the method call, the stack looks like this. The local variables from getSum have all been removed, and the local variable sum now has the value of 8. The next statement declares a variable named AVG and initializes it to sum divided by 2, which is 8 divided by 2, which is 4. So that looks like this. Next, we return AVG. So let's see how well you're following this. I'll give you 5 seconds to pause the video and think about what the stack looks like after we return from the getAverage method call. 5 seconds starting from now. Okay, the answer is that all of the local variables from the getAverage method, all of the green variables, will disappear. And the AVG, or average variable, from the main method will get the value 4. Here's what that looks like. What I showed you is an oversimplification of everything that actually happens, but it should give you a basic understanding of how the stack works. Sometimes, if you get a runtime error in Java, you'll get a stack trace with the error message. The stack trace tells you the methods that were on the stack in the order that they were called when the error occurred. For example, if an error occurred right before you returned from getSum, you would get a stack trace that read main, getAverage, getSum. This can be helpful in tracking down an error. The example we just saw involved variables of type int. An int is one of the 8 primitive types in Java. The values of primitive variables always reside on the stack, and it makes them easy to reason about. The stack is very orderly. Variables and their values are placed on the stack one after another, and they're removed from the stack in reverse order. The last thing to be placed on the stack is the first thing that's removed. That's why a stack is called a last in, first out, or LIFO data structure. There's another kind of program memory that is much less orderly than the stack. This is the area of program memory that holds objects, and it's called the heap. Now, maybe this is not such a fair representation of the heap, but the point is, when objects are created and put on the heap, they can go anywhere. It's like you just throw them on the heap and they land wherever they land. Of course, we're talking about computers here, so there is organization to it. But the main thing about the location of an object in the heap is that you know its memory address. We said that primitive variables reside on the stack and that their values also reside on the stack. Well, what about reference variables? A reference variable is so called because it references or refers to an object. A reference variable resides on the stack also, but the value that a reference variable holds on the stack is its reference value. Effectively, the reference value is a memory address, and that memory address is the address of some object on the heap. I like to say that a reference variable has 2 values, a reference value and an object value. The reference value is on the stack, and it points to an object that resides on the heap. For example, the type string with a capital S is a reference type. In this picture, str1 is a variable of type string. Since str1 is a reference variable, it has a reference value, which in this example is at 41. And that reference value is a memory address. The memory address is the location of a string object on the heap that contains the word hello. So the reference value of str1 is at 41, and the object value of str1 is the string hello. Now, one of the problems of thinking about things in this way is that you can never really know the values of the memory addresses. They exist, we just don't know what their values are. So instead of representing things like this, some people prefer to represent things with an arrow, like this. One of the interesting things about reference variables is that if two different variables have the exact same reference value, those variables refer to the exact same object. When this happens, we say that the variables are aliases, and that looks like this. You always have to be careful when two variables are aliases to the same object. That means that if you change the object through one of the variables, you have effectively changed the object value of the other variable. Now, there are cases when you may want to do this, but you should always be aware that it's happening. Two reference variables can have the same object value without being aliases. In this picture, for example, text1 and text2 point to two different objects that happen to have the same value. The distinction between aliases and independent object values is captured in the two ways that Java can check for equality. One way is with the built-in equals equals operator. This returns true for reference variables if the two variables are aliases. The equals method, on the other hand, should return true anytime two reference variables point to objects that happen to have the same value. Finally, you should know that every time you make an assignment from one reference variable to another, you are creating aliases. Okay, it's time for a question. If you have two reference variables, x and y, and x equals y, does that mean that x equals y using the equals method? Take 5 seconds to answer this starting now. Ready? The answer is yes. If two variables point to the same object, then the object should be equals to itself. It can be a little challenging to think in terms of the stack and the heap, but it's worth knowing these concepts. In the next video, we'll talk about the stack and the heap when we learn about the distinction between mutable and immutable objects.